There we go. Recording in progress. All right. Thanks, Zoom. All right, Taylor, go. Okay, somebody else go.
You put 148 minus 36.
Yeah, so it's always the final minus the initial. So 148 minus 36 would in fact be the first the first step. With this. Oh. You write a number 6. Yes. Well, you don't subtract it. So yes, simplify it. Yes.
I just moved this one. 148 minus 36, and I got the answer. I just moved this one to get that.
Okay.
112, and I moved this one for that. So how do we retake? How do we correct the test? Do you give us a copy of it and we redo it?
No. I've been saying the same thing all year. Where have you been? You do it on 7 previous paper. You have to correct all the ones that you missed, even if it's just a -1. You have to, when you do your corrections, you have to write the problem. You have to do all of the work. It has to be complete. It has to be correct. It has to be complete and correct. There are 2 possible grades you can get on your corrections. One of them is fixable because that's the grade. You can either get a fix or a 100. And if you get a fix, usually it's something small or something else. You fix the thing, you return in those same corrections, and you get 100 on it, assuming there aren't more fix. Questions on the words that just came out of my mouth, or no?
This is on the notebook paper.
That would be the easiest, best way to do it. You could do it on a blank piece of paper if you are very neat and careful, but notebook paper would definitely be easier. So yeah, you'd subtract that, you'd end up with 112. And then yeah, 112 over 36. And nope, not quite. You would think so, but no, because that's not a percent. It's because you end up getting 3 point. Whoops, that's not a 3. 3.11111111111, right? So in order to convert that to a percent, what would you have to do? Move the decimal back once, twice. So the percent change is a 311.1% increase.
I just forgot to convert it to a percent.
Does that answer your question, girl? Good. What other questions do we have?
I was off by 100.
By 100. Yeah, that's common. That's not, I mean, that's okay. It's an easy mistake to make.
So 12.
What other questions from the test do y'all have? Yeah. So for number 3, you're supposed, oh yeah, number 3. Yeah. That one, we definitely had some mistakes on. So number 3, you're supposed to convert 0.75% to a fraction. So what should we do to convert a percent to a fraction? Put it over 100. So we're going to put 0.75 over 100. We can't have that ugly decimal up there in this fraction. So what do we need to do to fix that problem? We should move it. If we move that one, what else are we going to have to do? Yep. So this equals, this is not reduced, but this equals 75 over 10,000. Now we need to reduce that thing. Excuse me. So what should we do to reduce it? True. So what would that be? Let's try it. What's 10,000 divided by 75? Why don't you need a calculator or scratch paper? I don't care which one. Yeah, I hoped that it was 75 as well. That's the first thing I tried, but 75 doesn't work. So if it's not 75, what should we try now? 25. Let's do 25. 75 divided by 25 definitely works. What's 10,000 divided by 25? So it'd be 3 over 400. All right. You probably punched it in the calculator. Okay. What else? Nathan, you were about to ask for what? Did you figure out which one you were wanting? 13. Number 13. Okay, got a swimming pool. I don't know if we recognize this, but on the note of studying, this problem is the problem from the study guide with the word swimming pool and different numbers. Just
I was like, oh, I remember this, but I don't remember the answer.
well, it wouldn't have been the same answer anyway because the numbers were different. But when I say study the practice test, I mean that's really what I mean. Just throwing that out there, you guys and gals. So the capacity of the swimming pool is 7,200 gallons. If the pool is 36% filled, about how many gallons, are in the pool? So what should we do?
You put 36 over 100 times 7,200 over 1. And then
That is definitely one way to solve it.
divide by 100.
So then you plug that in. 36 times 7,200 divided by 100. And what do we get?
2,592 gallons.
So a question that I don't ask often enough, because I don't, and it's a curse of knowledge thing, to be honest. But does that answer make sense? Does that look like about 30% of 7,200? Does that sound reasonable? Yes, it does. Okay. What else? Probably. Oh, so let's see. Oh yeah, the other crazy number.
I thought it was
On numbers 1 through 4, I gave 2 crazy numbers. True facts.
Wait, how much did you do? How much did you do? Yeah.
What I think this is about.
I also got 2,592. Where did that 60 even come from?
Because I just did 36 times 72.
Yes, because you can cancel this. Yes, also that also works. Sorry, I don't know where that came from. I probably said 92 or somebody else did too, I bet, but just wrote it wrong. Okay, so number 4. We're supposed to convert the number 650% to a fraction. So to convert a percent to a fraction, what do we do?
Which problem are we doing?
Number 4.
Wait, it's just write it in the simplest form.
As a fraction in simplest form. That means reduced. What did you say?
I said put
You did.
650.
It didn't work out real well on all your problems, did it? Yeah, you put 650 over 100. Sure, we could reduce it by 50. Sounds great. What's 650 divided by 50?
19.
And 100 divided by 50? 2. Now what?
We turn it into an exponent
How?
by doing 2 divided into 13, which is 6 and 1/2.
All correcto. All right. What other problems? I bet we could. Didn't we do 10 already? Oh, no, we did 11, right? Yeah. No, yes. Number 10. Oh, what percent? What? So number 10. What percent of 7 is 28? So
You do WP
WP over 100
times 7 over 1 equals 20. I add the extra 1.
you definitely do not have to. And I don't mind if you, so here's a word of advice on that. I don't mind if you put them. Just make sure your brain is understanding that 7 over 1 is 7, and it's all the same. The more you can think of why things work and how things work, and less about just step by steps, the better off you'll be in the long run. True facts. Now, what should we do?
100 times.
No. We should not do 100 times 7 times 28.
100 times 1 times 28.
Mm-hmm.
Oh, that's all.
So 7 WP equals 2,800. WP equals 400%.
Would you count it off if we didn't do WP equals?
Like if you use X or something?
No, like, just don't do, just put 400%.
No, well, it depends on how you solve the problem, but no, probably not. All right. What other questions do you have? Oh. LOLJK. Okay, so
That's the first of the ones that are at 30%.
yep. So put your tests away and let's start our next unit. And give a good college try of getting through as much of it as we can. Unit 8 is entitled something about linear functions, I'm sure.
I know.
Linear functions and graphing. Which is a great place to end this year in this class, TBH. It's a perfect alley-oop to Algebra 1.
We should just take it as long as we can. Let's not have fun.
You're definitely going to have a final test the last day of class. Going to happen.
How do we get back?
You know, I don't know that I've done it in this class period, but I've answered that question a lot. But Mr. Common Sense Man, how do you think you're going to get your test back? We'll make a guess.
Now.
That's one possibility for sure. It's more likely that I'll snap some pictures of it and send it to your parents or you or whoever, along with your end of year report. That'll say something like, my recommended grade is blankety blank blank for this student. My recommended next class is blankety blank blank for this student. This student is a really great person. They excel at pinochle. They are really terrible at multiplying times 2 or some sort of nonsense like that. Unit 8 is entitled Linear Functions. What did I say it's called? Linear Functions and Graphing. Yeah. And graphing. And the first lesson, so lesson 8.1. Yay. What are you yaying about, Miss Bryn? Oh, the test on the last day. That's probably what it is. I bet that's it. What do you want to bet? Lesson 8.1 is entitled, no, it's not a pre-lesson. It's a lesson 1. Oh, 8.1.0. Oh yeah, that's fine. Is entitled Functions. Which is the first truly algebra topic we've talked about. We've used algebra, but this is a big boy algebra topic right here. You can handle it. I have faith in your abilities. All right. So a function works like a machine. That's what a function is. It's the same, and it's the same definition, by the way, if we're talking about math, or if we're talking about science, or if we're talking about programming, or anything, any of those sort of related fields. This box is a representation of what I'm calling a function, my function machine. Okay. In the function machine, we put data in here. A data set. What is a data set, you think? Yeah, that's yes. Yes, thanks, snarky man. But what does that mean? Like if I was to tell you, if I said, give me an example of a data set or a set of data, what would you think might that be?
A spreadsheet of data.
Okay, so spreadsheet is a good idea. So what's on a spreadsheet?
Whatever you want.
It's yeah, whatever you want it to be. What we're kind of talking about in really generic terms, we're kind of looking at a list, right? A list of things, a list of numbers, typically we're talking about in math class. And then after we put it, then some sort of function happens. Something happens to that data set. And then my wallet and keys. That sounds disastrous.
I know. You just need your driver's license to
Why?
make a copy.
What are you doing copying my driver's license for?
The van rental.
Oh,
And then
terrible.
your keys to get the.
They're gonna make a copy at the place. Why do you need that?
No, I'm gonna only take them a copy. I only
Okay,
need a copy.
okay, fine. They only need a
Sorry,
copy.
everybody. Thank you. I'll bring it back.
Yeah, sorry. They're so mad about it. Look at their sorry faces. Okay. Pardon the interruption. Okay. After we put our data through our function, which is something happening to that data, right? After something happens to the data, then we get out a data set. A differenter one. Okay. So, and this right here is all a function really is conceptually. We put in a list of numbers or whatever else. We put in some sort of list and then we get out some other list. Now there's a little more to it than that makes it a function, because this could represent a function or a relation. There are some rules that make a function specifically a function. But before we do that, we could give some names to these two data sets. This first data set that's going in to the function is the input. Astonishing. So what do you think this other side is going to be? Output. My gosh, y'all are brilliant. So if we were to think about this in kind of a real life example that's less, it is mathy, but less conventionally mathy, we could have a function here. Let's make this function, what's y'all's favorite jam type? That's not what I'm asking, and you know it, man. What's your favorite jam? Apricot, sure. All right, so what is wrong with you? Have you ever had like homemade apricot preserves? Okay, well then you're weird. Okay, it's okay. All right, so we could have a function where the input set input some sort of amount of peanut butter, some amount of jelly, and some amount of bread. And then we put it in this function machine, and then the output Could be PB&J sandwiches. Machine. There you go. Everybody following along so far? Nothing super complicated?
So I put one brain cell into Garrett's brain and all the rest fall out.
No, that doesn't make any sense. Doesn't make any sense. Then Garrett would be dead. Okay. Let's put a little bit of math on it. And
Or we could just keep repeating that for the other questions.
yeah, we could do that. So if we had a set that looked like this as our input set. How about -5, 6 to -18? So if those were our possible inputs into some sort of function. You can, but I would use input as input. And our possible outputs are 6, 12, 13, -2. This is our output of our function, or not a function. Who knows? We're about to find out. The first thing before we make our connection, and we kind of start to see a little bit inside the function machine, is input and output have two other special names. The input, the set of all possible inputs, is called the domain of the function or relation, or both. The output is called the range, which is not the same as subtract the biggest number minus the smallest number range. That's a different range. We know which one we're talking about because context. Same as English words that are the same, but have different meanings. Or Spanish ones, which there are admittedly less of, but not none of. Okay. So this, if we do this right here, is a function. So if we input a 6 into this function, what are we going to get out? If we input a 6 into this function, we're going to get a 12 out. If we input a -18 into this function, what are we going to get out? -2. Always, right? If we put a 2 in there, we get a 13 out. This is an example of a function. Let's do another relation where there's an input and output, a domain and range, right? Let's have the domain be this set right here. Let's do -2, 0, 1, 2. And the output be 10, 11, 12, 13. So this is the domain. And this is the range. So the set of all inputs is the domain. Set of all outputs is the range. We're going to relate them. Oh, let's kill one of these. How about this one? That one's not in the domain. This is probably an easier place to start with our understanding. We'll make it more complicated later. Okay. And then we're going to do the relation like this. This picture, this bubble diagram is not a function. Why is this one a function and that one's not a function? So it's missing a number. What else is true about it? The 0 is pointing to two different things. So it has two possibilities. That's right, which is a problem because the definition of a function is a relation where for every possible input, so every member of the domain, essentially, there is one and only one possible output. So one way to represent a function we've already seen with these examples is called a bubble diagram, right? We can also have a relation or a function represented as a set of ordered pairs. Probably, actually, we've talked about ordered pairs in this class, right? Where we're graphing X and Y. And then you stick it on there, right? So we've seen ordered pairs before. So we're going to add to our OG kind of list because there's X and Y, right? So we already said input and output have two names. The set of all inputs is the domain. The set of all outputs is the range. Which one of those correlates to X and which one correlates to Y? It does. So the range is also, you could be described as the set of all possible Y's. The domain is the set of all possible X's. Doing well so far? Making sense? Any confusion? Okay. So we wanted to list a relation. So let's do an example with a set of ordered pairs. So here's our set. When we list a set, we use curly braces to list it. So a curly brace, and then we're going to list a set of ordered pairs. So the ordered pair 54, 112, and the ordered pair 56, 130. And the ordered pair 55, 145. And the ordered pair 54, 123. and the ordered pair 56, 128. So the question on this example, this problem is this a function or not? Is it a function or is it just a relation? You are correct. How do you know that? That's right. Two different 54s with two different answers. Also two different 56s. So the answer is no, because of this, that, and that. So is this a function? Is that one a function? Yes or no?
No,
Why not?
because there's two sixes.
There are two sixes, and that's a good catch, but one of them is an X and the other one's a Y.
So yeah.
So it is a function.
So would it not be a function if there were two numbers on y also?
It could be a function if the Y repeats.
Oh. So only if it's
Mhm. Mhm. In fact, one way that we phrase this test very often is if it's a function, X does not repeat. If X repeats, it's not a function. Okay.
when you're solving the function. The only one is if x.
Yep. Okay, what about this one? Let's see if I can do this well, or at least well enough. We're going to have a XY plane here. So is this a function? We're going to do some ordered pairs here. This will be easier on a proper grid with all the things, but so is that a function? And the way we do it for graphs, we use what we call a vertical line test. And what we're really testing for is, does X repeat? Well, on a graph, we can think about it like it's a vertical line. So I'm gonna do my best to draw it since we're recording and all those things. But if you draw a vertical line, you can do it with your ruler or a pencil and just kind of pass it over. And if at any point along the graph, it touches more than one place, like right here and right here, then it's not a function. So this is not a function.
So how does it translate to graph? How does it translate what's the vertical line test?
So the vertical line test is basically just looking for X repeats. So like if we were like assuming this is graphed like it looks like it's graphed, this point right here would be the point -1, 0, right? And this one right here would be the point -1, -1, 2, 3, 4, -4. So that's having the X part repeat. Yeah. So the vertical line test is just a way to test for a function visually. It's as we're looking at ones with lines and not just dots, it'll be easier. And you can get to where you can just look at it. Like if you knew about the vertical line test before I started this problem, you could have just looked at that bit and like, no, that's not a function. Right. Good job. Retroactive things. All right. So what about this one? What about this picture? This one is a piecewise relation. I won't say whether it's a piecewise function because we get to decide. Well, not decide, but figure out. You will not be asked to actually graph anything like this in this class, although it's not actually that hard. But you will be asked, is it a function or is it not a function? It is a function because it passes the vertical line test. What do those clear circles mean? It's a what? It's a clear circle. Somebody's deciding to be snarky. Somebody woke up and choose silliness.
No, I chose to go to the main source.
What does the one have to do with the other? Nothing.
No.
Nothing.
It was from the Bible story, and I did these songs.
So this one passes the vertical line test because even though there's something there, there's nothing there because a open circle means there is no point there.
So what's up?
On this part of the piecewise function, it doesn't exist there
So
So
why didn't we
it's-
just not put the circle in there?
because it's not clear that it doesn't include that point.
So you would solve this one by saying there's no sign up?
What? You just pass your pencil over it and see whether it touches more than once. So like if I was to draw vertical lines, right here it's touching once, right here it touches once, right here it touches once, right here it touches once, here it never touches twice, never breaks.
So what exactly is that symbol doing?
It's sitting there.
It's sitting there, it's making it look trickier.
Makes it look
Sorry.
Let's do it. Let's do another example.
It's stitches.
Another picture-y one. We'll do one with some more circles in it so we can make sure we're clear on the circlies. I should keep consistency and do it in pink. Here we go.
It's not a function.
That's right. This one is not a function. Because why?
Because the two filled-in circles are.
Yeah, so it is not a function.
What's the arrow for?
This relation keeps on going that way forever.
Okay. No.
It is kind of infinity. Not a function because this. Because it busted. Okay. Do we have? No, we don't have quite enough time for.
Open circle sign up, doesn't mean anything.
That's right. It doesn't mean anything because the open circles, this relation doesn't exist there. Yep. All right. Time is it? I bet we could squeeze that in. We're going to do it. We're going to make it work. That's good. It's good, good, good. Function notation. This right here. No. Is, well, has the potential to be the most confusing thing we talk about today. So I need you to strap your ears on. Okay. Okay. So this other is, I don't even know what you call it. Y equals notation. Y equals notation. So if we have something like y equals 2x plus 1, that's y equals notation. We've seen that. Have we graphed things like that in here with like finding the slope and y-intercept in here? I don't remember. Okay, that's fine. We will this unit. We'll make it to that before the end of the year. I'm pretty dang sure. Function notation. Is more descriptive. If we were to write this in function notation, it would look like this. F of x equals 2x plus 1. So there's a couple of things that I want to say with this. In this example, y is the same as f of x. Y is f of x. The other thing that I want to say, and this one is really important, really, 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 really important. And this is a number one confusion spot. Okay. And that is that f of x is stated, you say that f of x and it does not equal f times x. That's not what that equals. What this says is, so we say this f of x. We're going to write that. We say it f of x. So what this, and the reason function notation is useful is because it's more descriptive. And that's as far as we're going to get with function notation today. I'm going to give you some homework. And then I'll see you on Tuesday. Hey, we have only 2 more weeks left, boys and gals. Homework, page 402. Numbers 10 through 16. Evens. There isn't any function notation ones on that homework set, only the, is this a function or not? Goodbye. Both.